I welcome you to another tutorial. Differential equation, ordinary differential equation. In the last tutorial, we checked how to solve exact equation. We learned what we meant by saying that differential equation is exact or not exact, and we learned a very simple approach to solving an exact equation. In this tutorial, we want to learn how to solve a linear ordinary differential equation of the first order. Linear. When do you say differential equation is linear? We learned this in the first tutorial, where we talked about conditions for differential equations to be linear. If you still remember clearly, the first condition is that the dependent variable and all its derivatives must be of the first degree. The second condition, there should be no product of the independent variable and or its derivatives in the equation. Thirdly, there should be no transcendental function of the dependent variable or its derivatives in the equation. So for the linear ordinary differential equation of the first order, it has a particular form. So if you are asked what is a linear ordinary differential equation of the first order, just by saying that a linear differential equation of the first order is of the form dy dx plus p of x y equals q of x. This is linear ODE of the first order. As we progress in the course of the tutorial, we're going to learn about higher orders, but for now we are looking at the first order. So once you have this, solving this is not difficult. You need just two things, or let me say two formulas. And the first one enables you to get what we call the integrating factor. So just call it u. Our integrating factor u is given by exponential integral p dx. So once we get this, our u, we just say that uy equals integral uq dx. This is all we need. Uy equals integral uq dx. That's all we need to solve a linear ordinary differential equation of the first order. So let's check example. Find the solution of the y dx equals 5x minus 3 y on x, such that y of 1 equals 2. So this is automatically an initial value problem. So but let's get the general solution first before we consider the particular solution using the subsidiary condition. This is an equation. You can look at it very well. You can make it look like, assume the form of a linear differential equation, a linear ODE. So how do I mean? This is a term containing our y, so take it to this side. So we have the y dx plus 3 on xy equals 5x. And here we are. Got there, we can see this is exactly of the form where p of x equals 3 on x and q of x. So this is linear. So the next thing we do here is to obtain our integrating factor u. Obtain integrating factor u equals exponential integral p dx. Please, we should not forget this. So u equals integral of 3 over x dx. This gives us 3 integral 1 over x dx Let our focus be on the integral for now. 3 ln x exponential ln x cubed. This is u. So to bring down the values up, find the ln of both sides. Ln u equals ln exponential ln x cubed. Okay, so we have ln u equals ln x cubed ln e. Since the ln is log base e, so log base e of e is exactly 1. So we have ln u equals ln x cubed. So if ln equals ln, then u equals x cubed. So now we've got our u. The next thing for us is to use the other relationship to get the values of our y, and that is uy equals integral u cubed dx. Our u is x cubed, y equals integral x cubed 5x dx. X cubed y equals 5 integral x4 dx. That is 5 x5 on 5 plus c. That is x to the power 5 plus c. X cubed y equals this. So automatically our y equals, divide through by x cubed, we have x squared plus cx minus 3. And this is the solution. We've got the general solution, but since we are given the initial condition, we need to get a particular solution. So applying the initial conditions given to us, as y1 equals 2, the value we got is y equals x squared plus c x minus 3. So y equals 2 when x equals 1. Solve the differential equation x y prime plus 2y equals 4x squared. To solve this, let's try if we can make it to assume that form. Divide through by x, you have y prime plus 2 on x y equals 4x. And that's what we're talking about here. Y prime is same as the y dx. So let's write it so we can see it clearly. Okay, so our p here is 2 on x and our q is 4x. So this is linear. So next thing we do is we obtain our integrating factor u. U equals exponential integral p dx. That is exponential integral 2 on x dx. That is exponential ln 2 ln x exponential ln x squared u. You can look at this very well like when we did earlier. Ln u equals ln x squared. So u equals x squared. So having got the values of our u, integrating factor, to get the values of y would not be difficult. So let's do that here. Uy equals integral u cubed dx. Our u is x squared y, x squared, then y, integral x squared. Our q we got from the question is 4x times 4x dx. This is 4 integral x cubed dx. 4x 4 on 4 plus c. This cancels out. You have in x4 plus c. X squared y equals this. So our y By dividing through by x squared, we have x squared plus c x minus 2. Hope this is well understood. Let's give us some questions for us to play with. Solve the following differential equations: xy prime plus 3y equals 6x cubed, 2 y prime plus y equals sin x. Number 3, y prime plus 2 on xy equals x squared. Thank you. It's possible to also have some equations that are not linear but can be reduced to linear form. Just like in the previous tutorial, we learned about equations that do not look variable separable but can be reduced to variable separable. So the same thing for linear equations. Some equations don't look linear but can be reduced to linear equations. Some of those equations include Bernoulli equation and Riccati equation. We'll be looking at that in the next tutorial. Hope you join me then. Thank you.